Okay, today I want to implement a algorithm called genetic algorithm into Houdini, and the genetic algorithm itself, you can search it on the web, on the wiki probably. It's a type of evolutionary algorithm that you can evolve the behavior or property of some DNA through time by using crossovers and selections and mutation method based on Darwin methodologies. And in order to do that in code, probably in Python and Houdini, I have referenced a code from a Daniel Schiffman example code from Daniel Schiffman, which is a part of a book called Nature of Code. It's really a great book explaining all sorts of nature-inspired algorithm. And in this example called Shakespeare, he's setting a goal, a text to be or not to be, and he is creating a population of random words, which will be each of the random will be the DNA, and he's using those DNAs to select and cross over and mutate to evolve these words into the final words to be or not to be. So that's the code I'm referring to in order to use it in the Houdini. Maybe some people will find it interesting. Maybe you should look at it. I'm not gonna go through for this code. So in order to use genetic algorithm in Houdini, I guess there's two ways. One way is to use, maybe three ways. One way is to use Python exclusively, like just use Python to code the genetic algorithm part. Or second way, you can use Vex, which could be really fast but hard to maintain the data, especially when you have a lot of populations of DNAs, but could be really fast because it's multi-thread. And the third way I could think of is to just use a node without any code, which would be the speed itself would be the same as using Python, I think, because anyway you have to use for each loop or something like that. So for this example, I'm gonna use Python, which will be most easier for me, since I can refer to processing, and maybe some of the code I can just copy paste and change the syntax from processing to Python to use these. And it's not really a long code, so I think it's pretty easy to integrate it, translate it into Python. So I'm gonna use Python for this one. But the example that Daniel Schiffman is showing is a text, and I don't think it makes a sense to just have exactly the same code in Houdini just to simulate the text, the genetic algorithm with a text goal. since since Houdini is a 3D based software, I would like to use some kind of 3D properties in order to use genetic algorithms. So the goal here is to have a reference 3D model, which I chose it to be a dog 3D model, and I'm gonna use a metaball, a bunch of metaballs to trace this referenced 3D model, the dog model. So it's like having a first I'm just gonna import the 3D model so I can explain better. So first I have a geometry, and I'm gonna import the dog geometry here. It's in okay, first I'm gonna save this to okay, first I would like to import the 3D dog model, which is in this is a license-free 3D model. The license information is written on the description of the video, so please look at it. And if I look at this dog, it looks like these. Okay, so I'm gonna use this 3D dog, and I'm just gonna chop off his head, just his head, so that'll be much simpler. And I'm gonna use a metaball. The metaball simply makes a sphere into the point, the selected point. For example, if I have, let's see, if I scatter the dog model, I have a bunch of points. Maybe it's too much. If I have 100 points, and if I copy this metaball to a dog, and change the radius of the dog a little bit, so you'll have this kind of blobby creature. Right now I'm just using a scattered point from the base geometry, but what I would like to do is so these points are really determined by these object, the imported object, but I would like to use a genetic algorithm to find the best point position in order to represent the base reference, the dog itself. So it starts from really random scattered points on the 3D space, like in the text example from Shakespeare example from the Daniel Schiffman. It really starts from really random position and random size of the metaball, but time goes by, and if you calculate each frame, the evolving the DNAs of each point, so that each point represent as a DNA, and each frame it evolves and be much smarter to get closer to to make it look like a dog, a reference model. And that's what I would like to try using Houdini. So it's basically I'm just using a 3D model instead of a text. And the property of the DNAs is a position and the radius of the metabole. That's it. So let's try that. I'll delete these, and first I want to, right now the whole body of the dog, it's a bit too complex to make it with metabole, because you have thin legs, you have tails, and you have face. So it's a bit too much detail here, so I'm just gonna chop off just his head here to make it more simple. But first I want to rotate this to stand on the floor. Obviously. Okay, so -90 to X rotation, which will give it a correct position. And let's see. Let's put it into null here. And let's get some bound of the dog whole body and scale it down to the size of the face. So I'm gonna make it smaller on the height, something like this, and also on the depths. Let's look at the dog shade. Move up the boundary. Oops. And make it, place it to the dog face right here. Yeah, looks good. Okay, then I'm gonna use Boolean to chop off his head. I mean, make a Boolean difference. So normally if I do intersect, it should work, but somehow it's giving me a subtract result here. So if I change to subtract, yeah, so I got the intersection here. It's a bit weird how it work this Boolean is, but it's okay. Okay, now this here looks a bit weird. If I put normal here, would it? Not really. Maybe I don't need normal. Okay, at this point, let's change this to VDB. So, in order to make a fitness, like how well the metabole generated, the metabole made dog, the metabole based dog is close to the base reference model, I need to see some differences. What is the difference between the base dog and the metable based dog, the reference dog and the metable based dog? The easiest way to determine whether it is close or not is the volume difference, I think. So if the volume of the metable dog and the volume of the base referenced dog is close, then it is close to the metable based model is close to the base model, base 3D model. So I don't think I would like to think like that and make a fitness using that thinking. Okay, so in order to do that, the easiest way is to make a volume. First, I want to make it as a volume. I mean the VDB. So VDB from polygons to its head. And I don't want it to make it really detailed here because I know that using metable it's gonna be really blobby, so there's no meaning to make it really detailed. And since I have to make like some number of populations for DNAs, and it's not gonna be multi-thread because using Python it's gonna be really slow to calculate for each frame. So if I make it too dense like these, it's gonna make it like it's gonna take forever to calculate. So I'm gonna make it really low res to convert from polygon to VDV. So would like to put a parameter here, but let's say the voxel size is 1. Yeah, this is good. You can still see the expression of the dog, I think. You can feel the dog. So if that's so, that's fine. And let's then put it into the null here. Let's name this dog BDV. Okay. I also want to make a VDB for the boundaries because I'm gonna use it later. So this is the boundary box of the face here, so I'm gonna put it into the null as well. And convert it to VDB like I did for the dog face. And the same resolution, voxel size is fine. Okay, and let's have a null again. Name this box BDB. Okay. Now this is the basic model that's gonna be referenced to calculate it with the genetic algorithm. Okay, now next I'm just gonna jump into the genetic algorithm part. So the Python part, I guess. So before doing that, I want to make a null and make some parameters here, attributes here. Some attributes that I'm gonna use later on the calculations. And these attributes gonna be a property of a gene, which each DNA has, like each DNA has multiple genes, and this gene's property will be these attributes. So I'm gonna make 5 attributes. First, it's radius, which represents the radiuses, which represents the radiuses of the metabole. Okay, and it's a float. And size of 1, yes, it's fine. For the point, it's fine. Okay. And next I have X positions, which is a float as well. Oh, but it's a float array. And this one is also a float array, radiuses. And another one, Y positions, float array, Z positions, float array, and best index, which represents like which gene, which DNA is the best to fit. Which gonna come into detail, and it's integer, and it's fine. So I have 5 variables in a null object. Let's check it out. I don't see it. Whoops. Oh yeah, I see it. So radiuses, X position, Y position, Z positions in point, attributes, and best index in detail attributes. Okay. So the attribute itself is fine. Now I have these attributes. Also, I would like to have a bounding bounds position, like minimum position of the bounding box and maximum position of the bounding box. The bounding box itself is this one, I think. Let's name it B box. And if I look at the geometry spreadsheet on the point, you have like XYZ position for each corner point, and I would like to pick up the minimum, like XYZ the minimum and XYZ the maximum. So the minimum position XYZ to be the minimum is on the 0 index, And the XYZ to be the maximum is on the 6th index. So I'm gonna pick those up using, let's see, point attribute, point wrangle connected to bounding box, and change it to detail, run over detail, and have this attributes the minimum position and the maximum position to be in the detail attribute. And I'm gonna use this for later. 6th position. Okay, so if I look at the geometry spreadsheet, if I look at the detail, yes, I have the bounds max and bounds min. Okay. Let's name this bounds min and max. Now I have the info that I need here. Let's start implementing a genetic algorithm using Python. So in order to use Python and Houdini, I found a way to like transfer the Python instance between nodes using the session of the how library. So I'm gonna use that. So let's look at the code and let's use a Sublime so that it will be easier to code Python. So first let's import some libraries that I need, which is a default library from Python, so no need to install anything. First import math, import random, and import time. Okay, and I also wanna use inputs from node inputs. Okay. And let's make some utility function here called Remap. It's equivalent to fit in Vex, but it doesn't have it in Python, so I think I have to make it myself. So I have values, source, minimum, source, maximum, target, minimum, target, max. Maybe I'm gonna fast forward this part because it's pretty boring to see someone's coding, I believe. And if s max minus s min equals to 0, return tmax, else return value minus s minimum s max minus s min times T max minus T min plus T min. Now this should be correct. Let's try it. So if I have value 0.0, 0.1, and if I print remap value from 0 to 1 to 0 to 10, the result should be 1. I have saved this, close the sublime, apply, and I have an error. Sure. Yes, okay. Some mistake. Okay, I got one, so the remap function seems to work fine. Let's continue. So first I want to make a class called gene, which has a property of the radius and a position. So definition init self. So the initial position will be random inside a specific boundary. Now I have already made a boundary. I already have some boundary attributes, which I put it in the detail attributes before, so I think I can use that. So for the input, in order to make a new gene, will be position of bounds minimum and position of bounds maximum. So use these two boundary corner positions. I can make a point, I can make a random point inside of this boundary. Now first let's make an empty array which will represent the position of the gene, and for I in range 3, since there's only x, y, and z for the position, the value of the random position of the gene will be inside within the boundary, so it's position bounds min I plus well, I guess I can use remap that I just made. Remap so but no. Oh yeah, I can use that. Okay. So I have random number which will be from 0 to 1, and this will be the source boundaries, and the goal boundary will be position bounds min, and the maximum will be position bounds max. Okay, and so I'll have this value which is inside the boundary, and I'm gonna append this value inside a random position to make a random position. And finally, the self position, which will be the property of this gene class, will be random pos. And self radius, this will be much easier to do. So, okay, I think I also need to have one more parameters here. It's called radius bounds, which represent the minimum number of the radius and the maximum number of radius. And use remap to again fit the random value from 0 to 1 to radius bounds. Uh, 0 will be the minimum and radius bounds 1 to be the maximum. Okay. This should do it. Now this is good for the gene class. Now next, a DNA class. And let's make a constructor init self. So I also need a pulse bounds means and pulse bounds max as a parameter in order to make several genes together inside this DNA class. And maybe I need a radius bounds as well. And finally, number of genes. Okay, so there are several properties, variables you need to have in DNAs first. Most importantly, you need to have a fitness, whether to determine if it's close to the shape of the base model. 0 represents it's not close at all. 1 represents it's equal. And you have a bunch of genes. And let's have bounds min and bounds max as a parameter property as well, which you might gonna use it later. And radius bounds as well. And the number of genes as well. Okay, so right now the genes is empty, so when I create a DNA I want to also put a random genes inside a genes array by the number of genes. So for I in range self num genes self genes append gene. Let's make a new genes. The first parameter will be self pos bounds min self, the second pos bounds max, and third self radius bounds. Okay, should do it. So now I have a constructor. Now I need to make some functions in order to evolve using genetic algorithm, the basic functions. The first function you need is to calculate the fitness, but I'm gonna do it outside Python because you cannot use Python to control VDBs, I think. Maybe you can, but I don't know how to, so I'm gonna use it outside Python. So right here, I am gonna make a function called calc fitness, but here I'm just gonna tell the self fitness is from the point attrib value called fitness. So I assume that the point I inputted inside this function have already a fitness attribute called fitness, and I'm just gonna retrieving this fitness attributes and put it inside a fitness variable inside this DNA class. That's all I'm doing in this function. Now the next function you need is the crossover. So maybe I'll write from the selection. But DNA doesn't have a selection, so let's write crossover first. So what it does, you have yourself DNA, and you have another DNA as a partner, and you look at each other and randomly translate each genes, randomly pick up each genes from their cells, and like share it or translate it to each other to something like a mixing DNA. It's like from a father and mother you make a child using a DNA translation. So I'll name it child, and child equal DNA self post bounds min self post bounds max, and what else? Self post radius bounds and self num genes. So by doing this, I have right now the child is a randomly created DNA. I'm not gonna use it straightforward because it's just random. Next, I want to make a midpoint to determine where I would take the DNA from the father and where I pick up some genes from mother. So I'm gonna use a rand int because it's gonna be an index number, and the length between 0 to the length of self genes -1. Okay, and for I in range self genes, if I is bigger than midpoint, then child genes I will come from, let's say if the self is a father, and else the child genes come from a partner, which is in this case mother. And you have a child which has both father and mother's DNA, some part of DNA, some part of genes. And return this child. Alright, let's save this and check if there's any error. Nope. Seems okay for now, but if you cannot really check Python because you have to run it to check if it's working. So we'll check that later. Okay, let's continue coding. Alright, let's continue. So I made a gene class, so the next class I would want to make is a DNA class. So let's open the editor. Oh, I mean, I already made a DNA class. If I look at the functions, if I have all the things I need, no. I also need a definition called mutation. Mutate. To mutate, like randomly change its gene at some point, at some rate. So you need a mutation rate as a parameter for I in range. So look at all the genes inside itself. If random number is less than mutation rate, then self genes just replace the every genes it has, its DNA has to be a random gene. What was the parameter? Pos bounds min self pos bounds max and self radius bounds. Right. Okay, this is a mutate function. Another function I need specifically for Houdini, not for genetic algorithm particularly, is to change the attribute. I mean, change the property you have, I mean the genes you have to convert it to the property that it can be read in Houdini, which means either it'll be point attribute or primitive attribute or vertex or detail attribute. For this design purposes, I would like to give each point. I would like to give each genes to be a point, and the point have this attribute of position and the radius. So let's make a function called genes to geometry and have an input of point geometry, and let's make an empty array first. X position equals empty array, y positions, z positions, radiuses, and for I in range lengths of self genes, gene. Let's get the I index of genes and name it gene, and X positions, append gene position X. I mean, it has only position. It only has position with a 3 values inside. Lengths of 3 arrays, so the 0 will be the value that I need to append here, and y positions append gene position 1 z position append gene position 2 radiuses append gene radius. Okay, and finally set the point attribute to have X positions point set attribute value Okay, so each point doesn't really represent the gene itself, each point represents the DNA itself. Just realized. Z positions. Okay. Now that's all for DNA class. Now I need to make a population class which controls all the DNAs, like when it's gonna be selected and cross over the mutated. So the definition, first construct, I need a mutation rate, number of genes, number of DNAs, and I'll name it OnGeo, but it means a geometry library, which is similar to node geometry. I'm not using geo itself because each frame it refreshes the geometry inside this function, which means every frame it has different point or primitive or detail information inside here, so I cannot just use this which has called initially, because it doesn't change from by time to time if you write like this. So I want to make it as a parameter here. And time, this is for the random seed, and position bounds min, position bounds max, radius is radius bounds. Okay, it's a lot of parameters here. Now first, let's make a random seed using time and self. You have a parameter itself called generation to check which generation you are in. But in Houdini, I'm gonna use a solver to evolve the genes, evolve the DNA. So basically the frame number will be the number of generation. And self perfect fitness, well, I know it's not gonna be perfect forever since I'm using metaballs and I'm not gonna use that much of a number of points, so it's never gonna be perfect, but let's assume that the perfect fitness will be 1. And the self mutation rate comes from the input, and self mating pool, this is the array which you provide a number of mate coming from the current population in order to cross over the DNAs. And self DNA, this is the current DNAs that population has, and which its number is determined by the number of DNAs. Okay, so first let's make a random DNA here as an initial value. Number of DNAs you make, first you get a point from OnGeo, create point. Yeah, you create the empty point here first, and you're gonna attach some attributes into this point. So self DNAs append DNA pos bounds mean pos bounds max radius bounds what was the other input? Okay, and the number of genes. Okay. And let's call let self genes to geometry, which I have made it on, which I'm gonna make it later in this class. And I'm just gonna make it right now. Def genes to geometry, self, own geo. So let's first get all the points from the current input. I mean current geo self, which is from the first input of this Python node. And for I in range length of self DNAs, let's call genes to geometry inside for the DNA function. For each point. And that's all. So what was it doing is that it's transferring the genes information into points. So if when I make a initial, when I construct a population, it first make a point for a number of DNAs, then to it points to it to that points I'm attaching a attribute value from a genes, which is initially a random value. Okay, so the another function I need for the population calc fitness. Again, you need a own geo parameter input. Okay, you get all the points, and for in range lengths of self DNAs, you put for each DNAs calc fitness, calc fitness, which is this one. So it's just again transferring the fitness attributes from points to the DNA's variable. Okay, next. The important function here, definition natural selection. Gonna use this function to select a number of DNAs from the current DNA pool into a mating pool with the bias of using the bias of fitness. So first empty the mating pool, and for I in range lengths of self DNAs fitness equals to self DNA's fitness. and n equals to int fitness 100. So the fitness is in between 0 to 1 in float number. So I'm multiplying it by 100 to make it and change it to integer so that it will represent how many number of DNA you would have in this mating pool. And for a j in range of n, you add to mating pool the self DNAs at I position. Okay, it's a lot of functions here. And I also need a definition called generate. This is for the final evolving trigger that I'm gonna use to use the genetic algorithm basically. So for I in range self, look at all the DNAs here, and A equals integer of mass floor random value times length of self mating pool. Okay, let's check the syntax, and B will be the integer of mass. Another random value between 0 to the number of mating pools. So, oops, copy this and paste it here. Okay. So what I'm doing here is to randomly making an index A and B for the mating pool to pick up randomly. So you have partner A to be the A position of mating pool, and partner B to be the B position of mating pool. And the number of DNAs inside a mating pool is biased by the fitness, so if the fitness is really high for its DNA, there are a lot of same DNAs inside mating pool, so you have a lot of chance to get that from even from the number random index. So the child has a great chance to have its high fitness DNA using this method. And finally, you'll cross over partner A and partner B using crossover function to mix its genes. To make a child. And finally, do some mutate using the mutation late if at some point randomly change its DNAs in order to make it more diverse. And finally, replace the child with its current DNAs. And the generation gets incremented by 1 outside a for loop, of course. Okay, now I also need a Houdini specific function to get what is the best fitness from the current attributes variables you have here. So I'm gonna name it get best and first make an empty variable called best fitness and index to be 0. What I want to get here is the best DNAs from the current DNA pool array. So I'm gonna look through all the DNAs inside the DNAs array and look at each fitness and pick up the highest fitness value plus the index. Okay. So for I in range lengths of self DNAs, if self DNAs fitness is larger than best fitness, then replace the best fitness with the current DNA's fitness. Okay. And replace the index with the I. Oops. And on geo, I'm gonna set the attributes for on geo set global attrib value, which means a detail attribute, and best index to be index. Okay. Okay, think I made all the functions that I need for classes, population, DNAs, gene, and the custom function remap. So let's call a initialization first. So first thing I need to do is to get the pos bounds mean from the point attribute or detail attribute. So pos bounds means equals inputs from the first, the second input, and geometry. I'm gonna connect it later. And attribute value bounds min. Okay, pos bounds mux equal inputs geometry attrib value bound max. And the radius bounds equal, gonna use eval palm tuple from I'm gonna write a path for this one, obj geo1 what was the name? Okay, I didn't set any parameters for radius bound, so let's comment it out and save this first. Let's check if there's any errors, and there is an error. Okay, let's check invalid syntax 83. Class population. Okay. Simple mistake. And line 100. Okay, it's because I haven't connected anything here, so first I'll connect it. The attributes empty geometry with the best index with the empty with the added attributes inside the first input, and the bound min and max to be the second input. And now I don't have any errors, so it's fine. And I would like to add some parameters. Let's make a null and name it controller. Maybe color it to blue, and let's add some parameters here. Now the parameters that I need is first a number of genes, integer, it's fine, range from 0 to maybe 100. Okay, and another integers which represent the number of DNAs. And this could also be from 0 to 100, could be any number though. And I also need a mutation rate. Mutation rate. And it's gonna be from 0 to 1. But I don't think I'm gonna use 1, because if it's 1, it's like every frame, every genes will be random in every frame. So it's just gonna be a brute force calculation. Doesn't make any sense. And another one I need is a radius bounds, which is a float vector 2, since you only need minimum and maximum. Oh, why did I put label here? Float. Oh, okay. So I'll name it radius bounds, radius bounds. Float vector 2 is fine. The range is from, I don't know, maybe 0 to 100, I guess. And apply. And accept. So you have number of genes, number of DNAs, mutation rate, and radius bounds. And I'm just gonna type some numbers here which seem to work best for this example. And radius bounds to be from 1.5 to 10, which will be the radius of metaball later on. And right now I need to access this radius bound inside Python, which was on the last line here, radius bounds. So I'm evaluating the parameter value from controller radius bounds. Now I think it's correct. Now the other things that I need, I also need to pick up the number of genes parameter from the controller. So I'll use the whole eval palm to access. Just gonna copy this here. And genes and number of DNAs as well. Okay, and mutation rate. Okay, now I got the necessary parameters, necessary inputs to make a new population here. So let's make a new population. Initialize the population using mutation rate, number of genes, number of DNAs. What else? Okay, current geo. And a random seed value. So I'm gonna use the time times 1000 and make it integer as a random seed and pass bounds mean, pass bounds, max, radius, bounds. Guess it's all I need to input. And now you have initialized the population here. I wanna attach this or insert this population into session so that I can use outside this Python node. Okay, let's save this and see if it works. Nope. Okay, let's see. Line 40 post bounds has no attribute. Line 40 post bounds doesn't have any attribute. Okay, made a mistake. Okay, apply. Another gene instance has no attribute radius. Line 75 radiuses gene radius. Gene doesn't have. Oh, okay, I made a spell mistake. Population is not defined. 154. Population, another spell mistake. Sorry. Okay. Now I got rid of all the errors. Let's go to calculate next. So Next thing is pretty important. You need to calculate the fitness, since you are not doing inside this population, the Python node. I'll just name it init population. So I've gotta do it using the node based calculation algorithm, whatever it is. And I'm gonna use a VDB to calculate the volume difference between the base dog model, the reference dog model, and the metabol generated model. So let's make a subnet here, subnetwork here, since I'm gonna reuse it later on the solver as well. And I need to input some outside parameters to the second and third input. First, you need obviously a dog VDB, and also it's better to have a bounding box VDB as well. So you have the population. The population itself right now, if you look at the geometry spreadsheet, you have 100 points, which represents, each point represents a different DNAs, and each point has radiuses, x position, y position, and z position here. And you have like array of radiuses and x position, y and z positions. And the array represents, this array represents a genes which each DNA has. So if you set the genes number to 25, you'll have 25 random numbers inside radiuses and to the positions. Okay. So let's dive into the subnetwork to make a calculation fitness function using VDB, OpenVDB function. So the first thing I need, let's look at each DNAs using for each point. And first of all, what I would do is to make a wrangle. I want to change to detail wrangle. And what I would want to do is to set the point attribute, set each what did I want it to do here? So let's see, each point, I'm looking at each point right here. Let's make it single pass so that it will be easy to see. And if I look at the geometry spreadsheet, I just have one point which represents DNA. And okay, so you'll be having tons of radiuses, number of radiuses by the number of genes here. So what I would like to do here is to, okay, I got it. So in order to use these information for each DNA, so each DNA represents a scatter of points with the radiuses, so I want to visualize it here somehow. But now for this point itself cannot be a geometry because it already has information here and it has only 1 point, so I'm gonna put it to the second input so that it doesn't affect the main geometry stream. And here I'm gonna first retrieve the radiuses from the DNA point. Okay, since there is only 1 point, the index of the point will always be 0. And for float expositions, y positions, and z positions. Okay, and for look at all the radiuses. Doesn't have to be radiuses, it could be expositions as well. The number are the same because it's the number of genes. And you retrieve the radius from radiuses. You pick up the vector value position from x, y, and z positions. So I'm gonna use these arrays to make a new vector. Okay, and let's create a new point here, which represents the gene itself using the geometry. And attach the attribute radius to its point. Okay. Now let's see. Okay, point attribute. Okay, set point attribute. Okay, so now I have point. This is 1 DNA, and each point should have radius, which represents the radius of the metabole. So let's try that out. Let's make a new metabole here and copy. Use copy stamp to copy this metabole into these positions. Right now the radius is fixed to 1, so I would like to use the attributes radius here to scale these. So let's make a primitive wrangle here to scale, make a scale function. So first, let's get a transform from intrinsic prim intrinsic from 0 input, name transform, and at the prim index. Since the primitive and the point have same number right now, 25, so you can just say, oh wait, prim num. Well, it could also be point num, I think, but since I'm running over primitives, I guess it's better to use prim num. Okay, and since okay, so now I got that matrix transform. Let's scale that transform using scale and using the value of radius. Right. And set it back to the prim instinct to apply the transformation I have just did. Okay, I have error. Set prim in. Set prim entering sick. Okay. Still get an error. What is it? It's really hard to see what's going on with this error. Yeah, this is much better. Errors warning, no match function for such. Okay. Guess I'm missing the parameter here, and what I am missing is, of course, the transform. Okay. Think I did it correct. Did I do I see any changes? No. Doesn't seem like it's scaling, is it? Let's see, the point, radius, prim num. Let's see if I'm getting this value correct. If I look at, okay, it's 0, so I'm getting it wrong. The number, the name of the, okay, so I don't have radius attributes here because I didn't transfer it. Okay, now I have it. Okay, so this is a 1 DNA which represents the position of the point, position of the genes and the radiuses, and I want to use genetic algorithm to genetically evolve each points to be close to the position where it will construct, it will create a dog-like 3D model. Right now it's pretty random, doesn't look like dog at all, but it's fine since it's initial one. So if I look at the other passes, you'll see different random point position for each DNAs. Okay, it's fine. Let's bring this back to 0. And right now it's immutable and looks like a geometry. It looks like a mesh, but you still have 25 primitives, which represents immutable itself. So it still is immutable here. It's not yet converted into mesh yet. So what I want to do here is to convert immutable at this point to make it as a geometry, and it doesn't have to be that accurate. So the step size could be 2. It's pretty low poly, but in order to make it faster to calculate, you gotta be something like this. Maybe if you use only vex somehow, then it will be easier. It will be much faster to calculate, but it will be much harder to code as well. Okay, so now I got the polygon mesh. I'm gonna convert this polygon again to VDB. VDB from polygons. And let's set the voxel size to 1 as I did before. Yep. And here I'm gonna use the box BDB to make an analysis between the box and the polygons. First, what I want to do is that since the geometry should not go outside a boundary, I'm gonna intersect this polygon, the BDB here, with the box, so that I have all the necessary areas of BDBs. So I'll combine these two and set it to SDF intersection. So this is the area that's gonna be calculated. Okay, it's good. Now I'm going to use a dog BDB to first get a, let's call a combine BDB combine, and what I want to do first, is to get a difference between those two. SDF difference. So this represents that you have in between the dog VDB and the current random mutable VDB, the difference is like this. But the difference itself is not enough because there's also a volume outside the dog. So I'm gonna make another difference, BDB difference, and make the input on the other hand. So this represents the outside the dog, which how different it is. Now you have to analyze the value. One is this, and one is this. And the theory is that the total combination of this and this will represents the difference of the volume of a volume value between the dog 3D model and the metaball generated model. So less the volume difference is, much close to that the metaball geometry is to the dog geometry. So let's combine this together using union. SDF union. And finally, in order to calculate the volume, let's convert this to polygon. And let's use the measure to calculate the volume. Right. And I have the volume here. Somehow I have a volume minus here. Just a bit weird. I don't know where this minus value comes from. Maybe it's because of the normal position. Not sure what it is. Seem to have tons of surfaces. Well, hopefully the volume represents the volume of the whole geometry, even if it's saying minus. If I add it all, could it represents the whole volume? I hope. What if I change this to area? Well, but I cannot use the area because you cannot really see. You cannot really say that if the area is the same, the model is the same with this method. So let's try with the volume here. And hopefully it will give me a correct value, even if it's a minus. Okay. Now what I want to do is to, now I got all the necessary information here. I will add all the volumes here together and add it to this base DNA as an attribute, which will gonna represent the fitness. So point wrangle, and I'm gonna change this to detail again. And set the first one to be the first input, the measures to be the second input. And let's write. So I have total volume to be 0 for from 0 to and primitives 1, get all the volume value, and add it to the volume. And apply its value to point attribute. And if I look at it, at the point attributes, you have the volume, and it's the positive number, so I assume it's correct. So let's go with it. And finally, put it into the last for each end. So in this way, I can calculate all the DNA points to make a volume, which will be a fitness. And let's look at the geometry spreadsheet to see if there's a volume inserted for each DNAs, and yes it does. Yes it does. Okay, so next I will need another wrangle. This time I want to get the minimum and maximum of its value from the whole DNAs. So let's make another a point wrangle. Run over detail again, and let's have minimum volume to be something really big, and maximum volume to be 0 for an integer I to n points. The volume and get the volume first, and if the volume is bigger than max volume, oops, replace the max volume with the volume. If the volume is less than minimum volume, then replace the minimum volume with the volume. And apply minimum volume to minimum volume. Apply max volume. Right. And I have an error. Okay. Let's see at the detail. You have minimum volume and maximum volume. Yes. Correct. Okay. Now, right now the number is arbitrary. I mean, value could be any kinds of numbers here. The maximum could also be like 10,000 or 100,000. Minimum could be like 100 or 1,000 or something like that. So I want to remap these volume to 0, 1 in order to make it more easy to use it later on. To mutate, to select crossover. So what I would do next is, let's name this min max volume. Let's have a point wrangle again. Wow, it's taking really long to make this thing. Well, since it's coding, what can I say? Let's fit the current volume from the minimum volume that I made. Oops. To the source maximum will be detail max volume to 0, 1. Okay. And to make the generation comes faster, I heard it's a good practice to make the value a power of some number. May at this time, in this case, power of 2 square value, so that the value will be exponential. The fitness value will be exponential. The higher, the more easier to get to fit it. And last of all, feed the value fitness to the point attribute. And let's name this calculate fitness. Let's look at the point attributes, and yeah, there is a fitness from 0 to 1. Yeah, based from the volume. Okay. Last of all, this time I'm gonna make a Python component to feed the fitness to the population class, so that I can use them later on again, using them from the population. So I have node and geometry. First I need to retrieve the population from the session. And calculate the fitness here. Since I already have the fitness value inside a point, it makes sense to call this at this point and get the best. And again, feed the population into the session to update. And I have an error. 9 population instance has no attribute call. Okay, call fitness. Oh, doesn't have it. Okay, calc fitness. Global name point is not defined. What are you talking about? So you gotta go back to the initial population file to see what this means. 107. Okay, let's go back. Look at the line 107 self. Oh yeah, I don't have the points here. Huh. Oh, is she? So it should be points like this. Okay, and let's go back inside here. Let's write something and still have an error. 138, get best. Population instance has no attribute DNA. Okay, 138. 138. Past fitness, self. Okay, DNAs. Wow. All sorts of small mistakes. Okay, now I don't get a error. Finally. And what was I doing here? Get best. So I called get best, so if I look at the detail, I should have, yes, the best index, which will represent that which point is the best at this point. So obviously 43, index 43 has fitness of 1, so it's the best. Yeah, that's cool. Okay. Now I think I did all the things that I need here in this subnet to calculate the fitness. So let's go up and let's name this calc fitness. Okay. Now to the genetic algorithm solving the generation part using the solver. So the first input will be this one, which has all the DNAs. The second input is again the same as this one, the dog VDB. And the third to be the box. Okay. Well, I think. No, it wasn't. Was it? Let's look at it. Yeah, I think it's correct. Maybe I think it's better to replace the order here. So I'm gonna put the box to the second and the dog to be the third. And box to be the second and dog to be the third. Oops, I don't need a fourth one. No way. Right. And obviously I need to replace those as well. So the box to be here and dogs come here. Okay. Now, what else? So let's dive into the solver and let's get doing some generation here, finally. So in order to call the generate, again you need a Python and get access to the population from the session. Let's name this generate. And let's retrieve the population, house, session, population. And first, to make sure, calculate the fitness from current geo and the population natural selection to pick up DNAs and give it to the mating pool based on the fitness, and the population generate to actually evolve the DNAs from the mating pool, and then population genes to geometry to actually apply those information, the results value to the Houdini geometry, and again apply this population into the session, update the session population. Oh, again 117 in natural selection. Population instance has no attribute. Mutation. Oh wow. What is mutation pool? It's mating pool. Man. 117 self mating pool, obviously. Wait, did I save it? Wait, let's look at again. 117. Oh, mating pool, save. Apply. Is it really saved here? 117 again. Yeah, okay. And okay, another error. 61 in mutate DNA instance has no attribute postbound. Okay, another spell mistake. 61. Apply. Oh, another one. 129. Generate unbound local error. Local variable generation referenced before assignment. Really? 129. Are you sure about this? 129. 100 generation. Oh yeah. I have to use self generation to access. Oh, but oh yeah, this one. You always need to put self inside a class variable. Okay, no errors. Congrats. Then, last of all, I'm gonna use this subnetwork, copy this, paste it here, and calculate the fitness again. So the second input was box, so the box comes to second, the dog BDB to be the third. And the calculation pod completed. If you run this frame by frame, it should be calculating, it should be doing the evolving stuff for a genetic algorithm, hopefully. So for right now it's hard to check because it has only the DNA information. It doesn't have any geometry information here, so it's hard to check whether it looks correct or not. So let's combine these information into the geometry. Now, first thing I will do is to let's get the best index. Let's pick up the best index from here. 29 says right now, and pick it up from its points, which represents the DNAs. So 29 is here. So let's pick this up first, then visualize it. So I'll cover it with the group first, and let's make a point wrangle. But since I only need 1 point, I need to run once, which means I can run by detail, run over detail. And the first thing I need, okay, let's input this to first, not the first, the second, since I want to make from scratch. I'll get the best index and throat radius is at this index position, float x positions, point x positions. I'm gonna copy this for our y and z, y and z, y and z. Okay, and pick up the volume. I'm gonna use it to visualize using the text later. And for lengths, radiuses, So as I did in the fitness calculation subnetwork, I'm gonna go run over this radiuses or number of genes to actually make a point. So add point to the geoself, set x positions, z positions, set point attrib, and set the radius to the point attribute. At point radius is 1 I. Okay, and last of all, set detail attribute to add a volume attribute, volume value to its volume. To the detail, I mean. Now, so I have points. This is the best DNA at current generation with the points position with the radius plus the volume for this generation. Is this really the best one? Doesn't look like the best one. Looks like the maximum. Oh, it's so weird. It's a bit weird. I don't think it's getting the best one. Okay, let's go back to see to get the best. So, oh yeah. There's, okay, I think here, I guess, somewhere, yeah, here. So I was converting from converting the volume to 0 to 1, remapping the volume to 0 to 1, and I was using the source minimum volume, the maximum volume, and 0 to 1 as a target, but actually the minimum the volume is, the fitness should be higher. What's this? So what I should do is that I have to make it like these. So if the volume is close to the minimum volume, then the fitness should be high. If the volume is close to the high and the maximum, then the fitness should be 0. Yeah, this should do it. And since I changed here, I also need to change this one as well. Okay, now this should work, hopefully. So the best index is 62 at this point. The minimum volume is 4,243, and yes, the best volume is 4,243. Okay, that's great. Now, as I did before, I'll place the meta ball to the point position, and need to scale it, but I already have it inside here, so I'm just gonna copy it. And again, you need to transfer the attributes. Okay. Name is scale metaball. And again, let's convert the metaball to this time maybe a little bit high quality, high reso, since you want to represent it and render it afterwards. Yeah. And convert this to VDB from Polygon. Oops. And the voxel size should still, well, it doesn't have to be 1. Maybe 0.5 is fine. Okay. And now what I need to do is, again, you have to cut this BDV with the box, which is this one. So I'm gonna put the combine VDB combine, and put the box VDB here and get an intersect. Yeah, so this will be the final result. And again, convert VDB to Polygon. Looks pretty much low poly, but doesn't really matter. And let's have point wrangle. And from here, you have the volume here, which you don't have from later on, so you want to transfer this volume value to this one. So connect it here, and let's name feed volume, and detail. So let's retrieve the volume from the second input and attach that, apply that detail attribute to the detail of the first input. I look at the detail, yeah, I have the volume. Now, right now it's not on the 000 position, so I would just want to move this to 000 to make it easier to manage. So I'll use transform and use the centroid expression function to access the BB box, the bounding box of the centroid of the BB box. And this is for the X, and you need to do for the Y and Z as well. Okay. Now it's on the center. Now this will represent the evolved geometry. And this is so much mostly done for what I wanted to do. But then it's really hard to see whether it's close to a dog base model. So let's make a comparison this so that I can easily see whether it's close or not, whether it's really evolving, optimizing using genetic algorithm. So I have a dog geometry somewhere. Yeah, here. Yeah, I have this one. I don't like this here. So I'm gonna convert VDV from this one, which is used for calculation. Yeah. And let's place next to the geometry. And let's use the same transform to place it on the center first. And merge these two together. Right now it's mixing up, so let's move this a bit farther away from the the metabol generated model, something like plus 30. Yeah, it should be fine. And now it's also better to see in a number how close these models are. So we have the volume attributes in the details, so let's visualize that. So let's have a font, and I don't care about the font. Let's have the value from detail, volume, am I seeing anything? Maybe I need to increase the size, something like 5. It says 0, so obviously it's not getting what I need. Look at the expression again. volume. Okay, I need to make a null and name this volume. Alright, so I have the number here. Now let's extrude this a little bit. Maybe like 1. Did it extrude it? Doesn't look like so. Oh yeah, I have to activate it. Okay. Yeah, it's fine. It's fine. Now I need to transform it again, like these. And merge it with dogs. Now the position looks a bit weird. Oh yeah, since it's already on the center, I didn't need to use the expression at all. Maybe just a little bit of upward, like 13. Maybe 14, 15. Yeah. Okay, this is pretty much done. Now let's run to see if it's really evolving to really optimize to get it close to the base dog geometry. Cross fingers. So the calculation's a bit slow. I'm gonna fast forward it. If the number gets really getting lower, then it means it's getting optimized and getting close to the dog model. Okay, I'm gonna do like okay, let's end it right here. Well, it still doesn't look like a dog, but you can see that it's slowly evolving to look like the base model. A number represents the fitness is somehow decreasing from 4,000 to around 130 to 150, 60 is around that. So I guess it's working okay. But as you can see, it's a bit slow to calculate for each frame. I guess it's because using the BDV. If there's a way to use do all the calculation using Vex, maybe it'll be much faster. For now, using genetic algorithm, my way is to do like these. So if you know any better way, please let me know. Okay, thank you. This is all.